Feels so good 素敵なアフタヌーンプラチナみんな yeah 固めて転がす I love you いつでも smile for you 君だけにラブ Hey so 頑張らなくちゃお揃いの T シャツ、hey! 手編みのマフラーと、oh yeah! ハートウォーミン目白押し
Welcome back, everybody. If you haven't played that particular game before, I recommend it. That was Katamari Damacy. It's wonderful. I think it's only on the older versions of the PlayStation, but actually there might be a version of it that's available on the switch right now. So just a quick double check. Give me either a thumbs up or a check mark if everybody can see me and hear me okay. Looks like mostly checks. Okay, cool. Then with that in mind, we will go ahead and get started. Let's stop sharing that particular screen. We'll switch over to our notes for today. Stop sharing sound too. I wanted to make a quick comment about the quiz that's up today. One of the questions has an error in the solution. I'm not going to tell you which one because some of you still haven't taken it yet. But if you're quite confident you got that question correct and it's still grading it incorrectly, that might be the one that has the error in the solution. I thought I pushed out the fix for it earlier this morning, but it appears not to have taken. So I'm going to end up going back through and regrading those quizzes. So don't lose too much sleep if one of them appears to be giving you the wrong answer, even though you think that you got that one right. So those will get addressed in a little bit. Let me move a little bit of this around so that I can still see your chats. If anybody's got a chat, you can always shoot it to me in chat. And then I'm actually going to bring in one of the equations from last time's lecture that we're going to use again. This is equation 230. And so we're going to be spending most of our time today and tomorrow talking about how to go about using this equation to solve for the outlets coming out of an equilibrium reactor. And so it all ends up coming back to this particular equation in your book, which is, again, equation 2.30. And John had just briefly started to get to this equation towards the end of Friday's lecture. Omar, you get one attempt at the quiz. And so we're going to spend even more time here because the procedure gets a little bit more complicated as we're actually trying to solve something coming out of an equilibrium reactor. So just to summarize where we have been and where we're going to go, these two terms over here, those are our equilibrium constants that we've been working with, the K0 and the K1. Those are unchanged, right? We're just going to use those in exactly the same way we've used them for the last 2 or 3 lectures, and we're going to use those throughout the entire course. And they're not going to change very much. We saw one sort of small variation to it where if you are given a Ka at one particular temperature, you can use just the enthalpy of reaction to adjust it to some other temperature. But that is an application of exactly K0, K1, which is the shortcut equilibrium constant. And then what we had started to look at on Friday was this term over here, which is our activities terms. This is what we're going to be looking at more of today. We're going to keep looking at examples of that. This term in the middle, actually, we don't need that term. We never directly calculate that term. It is defined as K sub A, so you can imagine an extra little equality here. K sub A is defined as that particular term, but we never end up calculating this particular quantity all by itself. There is a method to do that that's given in the appendix in the book, and that would only be necessary if we were using what we call a Gibbs reactor, which is another form of an equilibrium reactor. But for our purposes, we never actually have to calculate that particular term. It's always a question of evaluating the left-hand side of this equation, which is our product of activities, to the right-hand side, which is some kind of an equilibrium constant. And so that's what we're going to go over today. A lot of this particular table is going to, or sorry, this particular side is just going to come straight out of table 2-1 or 2.1, which, by the way, anybody notice this little circular thing right here in front of me? Pop filter. It showed up a day early. We got ourselves a pop filter. So anytime that we need a product of activity coefficients, we're going to go, or sorry, activities. Those are not activity coefficients. We go straight into table 2.1. There's only 3 forms that we're really ever going to need in this class. We don't really use the solid form very much. We don't have a lot of solids that we're dealing with. And then table 2.1 is going to be aided by 2 other equations. and we're going to focus on one of them today and one of them on Wednesday. We're going to need to be able to express all of our outlet mole fractions as functions of the extent of reaction, which is what I will usually call squiggle. And this is defined in equation 2.31. So we'll come back to 2.31 later today. And then on Wednesday, we're going to look at what if we want to do this, express each of these in terms of conversion. Conversion from CENG 100 would have been the letter F. And so you've probably seen this previously written as something like F sub A. A little bit of nomenclature that shows up inside of reaction engineering is that we don't call it F sub A anymore. We call it X sub A. But that means conversion, right, instead of extensive reaction. And so we're going to see, we can do almost exactly the same thing with conversion as we can with extensive reaction. It honestly just makes the equations look a little bit nastier, but conversion happens to be a helpful parameter for quickly evaluating systems faster sometimes than squiggle. And so this is equation 238. And so today we're going to focus just on this one. How do we use it with squiggle? And then tomorrow, how do we use this with conversion? The other two equations up here, I guess I should note, for K0 and K1, those are the same old 2.24 that we've been using and 2.25. And then that shortcut version that John had gone over yesterday, where if you're given a K and you want to adjust it for another temperature, that was 2.29. Right, so that side's not going to change. That side looks pretty much the same. So let's take a look at what would happen with an equilibrium reactor. So we'll draw a little equilibrium reactor here. We're going to introduce a little bit of nomenclature for reactors as well. And this nomenclature will follow us for the rest of the course. If we're running something at equilibrium, we're usually going to denote it as EQ. And so the further we get into the class, we'll see that we're going to start putting some superscripts on things or subscripts. It depends on what we're doing that say EQ, which is supposed to remind you that it's at equilibrium. The stuff going into the reactor is always denoted with a circle, a 0. If, for example, the inlet temperature is T sub 0 and the reactor is operating isothermally, then the outlet temperature will be T. Similarly, if the inlet pressure is P sub 0, then the outlet pressure will be P. And so these subscripts here, the zeros, those are implying the inlet conditions, right? So 0 means the inlet, and then the outlet stuff just doesn't have a subscript on it at all. It's pretty rare, with perhaps the only exception being on the project, that we will have more than one stream going in and one stream coming out. And in fact, that's not uncommon for how a reactor is actually assembled, because often these things are very expensive. They're working at very high temperatures and very high pressures, and it's very difficult to control a reactor like that if you've got some feed coming in this way and some feed coming in this way and more feed coming in later on in the reactor. And so most reactors tend to have one inlet or one outlet, one inlet and one outlet, although that's not required, but it's very common. If we have any material coming in, we'll denote that as N sub I with a little 0 on it. And so again, that means the moles of component I coming in. Nearly the entire class will be done in moles, although your project will be in mass, because there are some fields that work in mass, and so that's a good one to practice. Anything coming out of the reactor is N sub I. And then a few terms that you should remember from, boy, I don't know, probably physics. I know 100 and 102 would have done it. If something is isothermal, that means that T is equal to T naught. And if something is isobaric, that means that the inlet pressure is equal to the outlet pressure. And we will relax those requirements as we go. But in terms of the equilibrium reactor, this will always be true. So this is always the case. For any equilibrium reactor that we deal with, it'll also always be isothermal and isobaric. That does not mean that the pressure is atmospheric pressure. It doesn't mean that the temperature is room temperature or anything like that. The temperature and pressure can be anything that we want them to be. but it's constant, right? So whatever's coming in has the same conditions as whatever's coming out on the other side. And then the process of sort of quote unquote solving for an equilibrium reactor is a three-step process. And I'm going to say that it's three-step, and then I'm going to cheat my way out of it. Let's make sure that this is black. So three-step process for an equilibrium reactor. This will, the general approach here works anytime that you know what's going into it and you need to know what's coming out of it. If you have, a different type of a question where it's saying like, we need to achieve a certain conversion, or we need to achieve a certain outlet condition. So tell me what like the temperature is, or tell me what the inlet composition needs to be. It still kind of follows this approach. It's just a matter of probably guessing and checking, right? You sort of assume something and then go through this approach until you find out whether you got the right approach. But if you know what's going in and you just want to know what's coming out on the other side, and you're given stuff like the temperature, then this procedure works just fine. The way that I'm going to cheat is I'm going to put a step 0 on there. And the reason that I'm doing that is because step 0 usually comes to you pretty naturally. It's write the reaction. But the reason that I explicitly write that as a step in the reaction or in the solution procedure is the choice of stoichiometry matters. And so if not given, because the choice of stoichiometry matters on some of the steps, but not on the final result, if, for example, I'm asking you to calculate intermediate values before we're actually asking you to calculate the outlet values, if you change the stoichiometry from what I gave you, your intermediate numbers will look different, although your final answer will be the same. And we're going to demonstrate that in today's class. We're going to see what numbers end up being different and then which numbers end up being the same. Short answer, any number that's calculated based on stoichiometry is going to be different for different choices. But the parameters like outlet, temperature, pressure, and moles, those will not be a function of stoichiometry. So we're going to do exactly one example in two different ways, just to show you which ones are which. So if you're not given the reaction, write it down and stick with that stoichiometry. Use that stoichiometry everywhere for the rest of the equilibrium problem, and don't switch around stoichiometry. So the actual first step is one that we've already been doing, which is calculate K sub A, right? And in all cases in this class, we're going to approximate Ka as Ksc. But I'm usually going to call it Ka because I want you to know what you're actually calculating. It's not that you have to make it equal to Ksc, it's that you have to make it equal to the equilibrium constant Ka, and we just happen to be abbreviating that with Ksc. The second step that you're going to do is write all of the activities, so A sub I. And for this, the process is actually pretty straightforward because we're just going to go over to table 2.1, and we're going to look up whatever the activities are. We're going to write them down. And then the last step is actually to solve equation 2.30. 2.30, 2.31, 2.30, yeah, this one, right? That's our balance equation up here. We're going to end up solving that in most cases for the extent of reaction, squiggle, although as we will see in Wednesday's class, we can also solve for conversion. The approach is almost identical, it's just the conversion equations have a couple more parameters floating around inside of them. Do you spell it as squiggle? Yes, that's usually what although, so this term, if I use this in MATLAB, you'll usually see it referred to as its Greek name, which is Xi, which is very hard for people who don't speak Greek to say. Sometimes you'll see it pronounced as Xi, but it's supposed to be like a K sound and then like a C, like Xi. Anyway, this particular equation, if you're curious, why are we using that one? Equation 2.30 is the second law of thermodynamics, right? If you go back through the book and see where that was derived from, we started off by saying that equilibrium is defined at where the change in Gibbs free energy can't go down anymore, which is at its minimum. If it's at its minimum, we'll remember from I don't know, Calc 1 or something like that, that its derivative is 0 at that point. And if the derivative is 0 and you are clever enough, thank goodness that thermodynamicists are, you can eventually come up with this expression 230. And so it's just a statement that Gibbs energy has been minimized at equilibrium. That's the second law of thermodynamics. And so that's why we are solving equation 230. Right, and so these are the 3 steps, 3 and a little bit, right? 3 plus step 0. In most cases, we won't worry too much about step 0 because very often the equation will be given to us already. And so we won't have to worry about whether or not we're writing down the stoichiometry because we'll just use it the way that it's given. So let's take a look at an example. This example that we're going to look at, we're going to continue our example of the Haber-Bosch process, or maybe it might be Haber, I'm not sure. But this is, as John said, an amazing reaction because it is the core of all of our fertilizer, which feeds a very large number of people. And so the system that we're going to set up, we're going to have our little equilibrium reactor here, have some feed going in, something coming out the other side. It's windy over here. I hope that wind isn't coming through too much on your side. The Haber-Bosch stoichiometry that we're going to use, this will actually be step 0 over here. Will be 3 hydrogen plus some nitrogen, goes back and forth to 2 NH3. The little double arrow sign here in the center, that's important because occasionally if I give you a reaction, it'll only have a single arrow, and that means it's an irreversible reaction, and so equilibrium doesn't matter for an irreversible reaction. And so just keep an eye out for that particular symbol. I'm just going to do a quick atomic balance here. So I've got 2 nitrogens and 2 nitrogens, 6 hydrogens, 6 hydrogen. So we're good to go. What does H-B mean? Oh, sorry. H-B is the example that John was working on, which is the Haber-Bosch process. It just means how do we get hydrogen and nitrogen to form into ammonia. It is actually an equilibrium limited reaction in a lot of cases, so it's appropriate to model it in an equilibrium reactor. Our equilibrium reactor, we're going to change it a little bit from John's example, and only because the math works out a little bit easier. So we're going to make our temperature 400 K and our pressure 101 kPa. John used a slightly higher temperature, and I will, if we get enough time towards the end, I'll talk about what this is or why I chose 400 instead of a much higher temperature. Can we use an equilibrium reactor for an irreversible reaction? No. The assumption of an equilibrium reactor, if you want a picture of it in your mind, think of a reactor the size of the planet, right? It's absolutely enormous. Everything that goes in there will get all the way to its fullest degree of completion. And so what that means for an irreversible reaction is that the reaction will go entirely to completion. Usually it will have, that means that it will have 100% conversion of the limiting reactant. And that's the case for an irreversible reaction, only in very limited circumstances, right? Only when the reactor is very large or the reaction is very fast. That's not the case for an equilibrium reactor. We don't have any notion of, in an equilibrium reactor, there's something forcing it to go the opposite direction, which is why we're using the double arrow here. The reaction is actually happening in reverse. And so no, we would never use an equilibrium reactor for an irreversible reaction. It just wouldn't show up. We're going to feed everything in a stoichiometric ratio. So we're going to feed 3 moles per second of hydrogen and 1 mole per second of nitrogen. And then we're just going to assume that everything else comes out. So we're going to get a little bit of hydrogen, a little bit of nitrogen, and a little bit of NH3. And we're going to assume it's all gas phase. Right, everything coming in is gas phase, everything going out is gas phase, and so that'll help us a little bit. That's where we would start. The first actual step of sort of solving for what would the outlet composition be is, if we scroll up a little bit in your notes, right, we just did step 0. That was the one that we just did a moment ago. We're now on to step 1. So we need to calculate K sub A. In order to calculate K sub A, we do exactly the same thing that we practiced in the last few lectures. So K sub A is going to be approximated as K0, K1, which I'm not going to go through that math all over again, but you're welcome to double check it. 43.957. Let's clean up my 5 a little bit there. 957. That's one point that's a little bit different from John's example, just because I picked a different temperature. But the reason that I picked a different temperature, again, is one that I'll get to later on. Now we have to get, according to step 2, we need A sub I for all species. It can be a little bit helpful when you're setting these things up to give yourself a table like we've used. Ooh, we've drawn a lot of these tables by now. So I'm going to give us a little table here. Species, stoichiometric coefficient. I'm going to say the moles of I coming in. I'm not going to, actually, let's see. Yeah, we can go ahead and write the units on here, which is going to be moles per second. And so we'll have H2, N2, and NH3. The stoichiometric coefficients here will be -3, -1, and +2. And just by pure convenience, we had 3, 1, and 0. Keep in mind, these two are not at all related. It's not like it's always -1. It just happened for this equation or this example because that's the way that I chose it. And then we're going to figure out the activities for each one of the species. These are all gas phase. And so if we go over to table 2.1, what we will see that is every single one of these activities is going to be equal to Y sub I times the pressure of the reactor divided by this P circle term. The P circle term, it's always something that's close to atmospheric pressure. It's usually defined as equilibrium or as atmospheric pressure. It just depends on the units that you're using. And so for the references that I had, this was 101.325 kPa. This is the reactor pressure. So for our case, this happens to be 101 kPa, which is really, really close to 101.325 kPa. And so these two terms will cancel in every single one of them, right? P will be very close to P circle in every case, and so we're just going to ignore it. That's usually okay if you have small pressure changes, or sorry, if your pressure is close to the standard pressure, which is P circle, within like 10%, 20%, something like that. If you're operating at like twice atmospheric pressure, 3 times atmospheric pressure, then you should probably include that term. But we're really close to atmospheric pressure, so those two terms are going to be really close, right? It's going to be 101 divided by 101.325, which is going to be like 0.999999. And so it won't make a big difference. And so ultimately, the only thing that we're left with that we're interested in for the activity is going to be the Y sub I for each term. And so our activity for hydrogen is going to be Y sub H2. Our activity for nitrogen is going to be Y sub N2. And our activity for ammonia is going to be Y sub NH3. And so this now becomes the question of how do we actually find those mole fractions? We do exactly what we did in CENG 100 and probably again in CENG 102. Do we always assume an ideal gas in this kind of a question? Yeah, it always behaves ideally as an ideal gas. This activity, though, can be very complicated if you choose to model your solution as a non-ideal solution, but everything that we have is going to be ideal. That assumption is actually baked into table 2.1 already, and so don't try to switch the two of them. Does the activity refer to the products? That's a good question. So how do I know whether or not something is referring to an inlet or an outlet? What you'll see here is that there is no subscript of 0 on any of these, right? But if I'm referring to my inlet, there's a little subscript 0 on each one. So because there is no subscript 0 on these activities, there is no little 0 that sits right here. These are all referring to the outlet. And the reason for that is because we assume the equilibrium reactor is well mixed inside. So anything inside the reactor is the same as what's coming out of the reactor, which is an assumption we get, we revisit with our next reactor. So how do I know if it's inlet or outlet? There's no subscript 0 on here. And so these are all referring to outlet conditions. That was a good question. Yeah, keep that one in mind. So how do we calculate mole fractions? Well, the mole fraction of any component, y sub I, is equal to the moles of I divided by the total number of moles, right? That hasn't changed. That's our basic definition of mole fraction. The next part is something that came up in CENG 100, and I'm guessing it was probably used just a tiny bit in 102. But the amount of moles coming out is equal to the amount coming in plus the stoichiometric coefficient of that species times the extent of reaction for that particular reaction. And then the total number of moles is the total number of moles coming in plus the extent of reaction times the sum of all of the stoichiometric coefficients. And this is exactly the same thing that we were using previously in CENG 100. This little term comes up a lot, the sum of the stoichiometric coefficients. So we have a special symbol for that. We call it lowercase delta. So if you're creating variables in MATLAB, we would call that one lowercase delta. If you have not brushed up on your CENG 100 lately and you want to know where these are coming from, not a problem, got you covered. This is equation 231 in your book, and this is equation 2.34. But when you're looking at these, just try to keep it, if they're given in a way that's not familiar to you, try to keep in mind that they are the same thing as CENG 100. And so if you pop open those notes that you had for CENG 100, you should be able to sort of link the two of them because they are directly related to each other. And so now we will take each one of these and substitute it into our product term. And so our product term is the product of A sub I raised to the stoichiometric coefficient for each of the terms. Remember, the stoichiometric coefficients are negative for reactants and positive for products. So all of the activities of the products end up going on the top. For example, A sub NH3 raised to their powers. And since all of the exponents are negative, or the stoichiometric coefficients are negative for reactants, they end up going onto the bottom. So we've got A sub H2, and that one is cubed, and A sub N2, and that one is just to the 1, right? There's nothing else there. If we substitute our mole fractions, that's Y sub NH3, and Y sub H2, and Y sub N2. And so now we're going to take this expression that we have up here, this fairly lengthy one, and we're going to substitute one of those for every one of the terms that we've got in here. So you can very quickly get some fairly large looking equations, but it's usually not too bad. The way that I usually like to start off is I know that the actual moles of everything are just going to show up in exactly their same place. Right? The N sub I is going to show up in exactly the same place. So I'm going to have the moles of NH3 coming out squared divided by the moles of H2 coming out cubed times the moles of N2 coming out, just raised to the 1. And now each one of those also happens to have an N sub T carrying along with it, except it's inverted. So the end result here is that we have N sub T squared. Right, this particular term, the NH3, is N NH3 divided by N sub T, and then you square that. And then each of these terms down here is also all divided by N sub T. And so if you work out the powers there, you end up with this particular expression, right? It looks like N sub T. And then our step 3 to actually solve this is to use equation 230. And so N sub NH3 squared divided by N sub H2 cubed times N sub N2 times N sub T squared. According to equation 2.30, this has to be equal to the equilibrium constant K sub A, which for our case is 43.957. right? And now we have to come out with a way to actually solve this. N sub t is the total number of moles. So N sub t is that term. N sub t is this. The reason that N sub t shows up is because it's part of Y sub I, and Y sub I is how we get our activities for things that are in gas phases. So it's a bunch of algebra is why that term came up. If we expand this, and this is where I most often make my mistakes when I'm doing my algebra, I have 43.597. And if these numbers don't look familiar to you, just double check your CENG 100 notes. So the amount of NH3 leaving the system is the amount of NH3 that came in, plus the stoichiometric coefficient of NH3 times squiggle, or times the extent of reaction, and then we have to square that. And then that times the moles total. The moles total coming out is equal to the moles total coming in, minus that delta times the extent of reaction, which is squiggle again. Moles of NH3 coming out is coming in minus stoichiometric coefficient times squiggle, and this case is cubed. And then the moles of nitrogen coming out is moles of nitrogen coming in, which is 1, also minus squiggle. Right, so this expression is one big function of squiggle. The way that you go about solving this, whatever you want to do. If you like using your calculators to solve these things, go for it. I usually suggest that you solve them in MATLAB, which if we have enough time at the end of class, we'll check. But however you choose to go about solving that, it's one equation and one unknown. And so you'll have a single equation to solve. And so the result for this, if I use MATLAB, or whatever you want to use, is that squiggle should be 0.667. Squiggle does have a unit associated with it, and it's a very strange unit. It's one that I've actually wanted to try to get everybody away from, but boy, is that an uphill battle to change the name of a unit. Mole reacted per second. And so the reason that I point that out is because this is specific to the stoichiometry that you chose. This is specific to the stoichiometry. So if you choose a different type of stoichiometric coefficients or a different scale, right? You double them all or cut them all in half, you will get different K sub A's, you will get different extensive reaction. All of those will end up being different. And so you just have to keep in mind that those things will be different, because when you are, for example, comparing answers to something else, you may have a different intermediate example. However, the stoichiometry does not have an effect on what's coming out of the reactor, right? Intuitively, it should not matter how I write these stoichiometric coefficients. If I write mine as a factor of 2 higher than you write yours, it does not change the equilibrium location, right? The equilibrium composition should be exactly the same. And indeed, it is the same. And we're going to have just enough time at the end of class to show that. If we use our stoichiometric table, or our magic table, as it's sometimes called, and we write each one of these down, the species that we have are H2, N2, and NH3. If you have enough space, you could probably just tack all this on at the previous page, or the previous table. I just run out of space. And so coming in, 3, 1, and 0. And so coming out is now 3 minus 3 times extent of reaction. And in this case, that's 0.967. The amount of nitrogen is 1 minus the extent of reaction, which is 0.322. And the amount of ammonia coming out is 2 times squiggle, which is, I think, 1.355. 1.355. The total number of moles coming out, we've already actually used this. It's 4 minus 2 squiggle, or 2 extent of reaction, which is 2.644. And now if I want the mole fractions, Y sub I, those are equal to n sub I divided by n sub t. So you'll notice we're using the same set of equations that we were using within the actual equilibrium reactor, which is to be expected, right? It's the same set of units. We're talking about the same reactor. And so here our mole fraction is 0.366 and 0.122 and 0.512. And so if we wanted to ask what is the mole fraction of everything coming out, or what are the moles of things coming out, that would be asking what's y sub I or what's n sub I. Usually we don't care about the n sub t sitting over here. If we had 4 moles coming in, how do we end up with 2.644 leaving the reactor? That's a good question. Moles are not conserved. And so anytime that we have a chemical reaction, we should not expect the same number of moles going in as we do moles coming out. But we should expect the same amount of mass. So if you multiply each of the incoming amounts by their respective molar masses and compare that to the product of the outgoing amounts and their molar masses, that will be equal. But moles are not conserved. So the same number of particles coming in is not the same number of particles coming out. If, for example, you think about if we have one molecule going in and inside the reactor, we break that molecule into 2 pieces, we now have 2 coming out the other side. And so it's not the case that moles will be conserved. And so that, that would be our question of, if we were trying to answer, that would be our answer to the question of, if an equilibrium reactor was operating under those conditions, what would the outlet be? We just calculated that. There's still no accumulation, correct. So what if the stoich was different? Suppose at step 0, somebody else had written 3/2 hydrogen plus 1/2 nitrogen goes back and forth to NH3, right? Conceptually, we know that, or we should expect that whatever's coming out of our reactor, it ought to be the same thing, right? Just because I changed the stoichiometry, it shouldn't change what's actually coming out of my reactor. So we should be able to prove that to ourselves, that is indeed the case. If we were to go on to step 1 here and calculate K sub A for this reaction, it would be 6.63. That's not the same as the K sub A that we saw before, right? The K sub A that we saw before was 43.957. The reason that it changed is because the stoichiometric coefficients changed. And so therefore the number is going to change, right? That seems reasonable. The next step also changes, right? Where we have the product of A sub I raised to the stoichiometric coefficient of I is equal to now the activity of ammonia, still goes on the top, raised to its stoichiometric coefficient, divided by A sub H2 to the 3/2 and A sub N2 to the 1/2. That is quite a bit different, right? These coefficients look nothing like the coefficients that we saw before because the stoichiometry has changed. But the great thing about this is they have changed in a way that is exactly balanced by the change in the K sub A that we have up here. And so all of these numbers will change, right? The intermediate values that we calculate along the way, they will all change. If we were to try to solve this equation, right, if we were to set the K sub A equal to the product of the activities, we would end up with squiggle for this system is 1.355 mole reacted per second. That is also different, right? This term is now different from the squiggle that we got before. The squiggle that we got before was like a 0.6, something like that. I think I have it, yeah, right up here. Yep. 0.667, right? That was with a different stoichiometry. I have now used a different stoichiometry down here and gotten a different value of the extent of reaction. If, however, I put those into, actually, there's no 4th step on here. If I now use that squiggle and calculate what's coming out, right? If I say species, nu sub I, everything coming in and everything coming out, so n sub I is n sub I 0 plus stoichiometric coefficient times the extent of reaction. this is the part I think it's really neat. And I had to do this when you're sort of reminding yourself how all of this stuff works. I have to always do it like 2 or 3 times just to show myself that like this, and the fact that you can multiply things by their molar masses and get that there is no change in the total mass going in versus total mass going out, I think is a really neat thing, right? It's conservation of mass. I should not be so impressed, but I'm impressed. So if we change these, actually, let's just ignore the stoichiometry. We know what that was. Actually, it might be helpful. This was -3/2. This was -1/2. And this was +1. We didn't change anything else about the reactor, right? We kept everything else the same. And so now, sure enough, if we take 3 minus 3/2 times 1.355, we get exactly the same thing that we got before, which is 0.967, right? Compare this value, the amount of hydrogen coming out of our system, 0.967, scroll up to what you had a moment ago, it was exactly the same thing, right? 2 different stoichiometries should give you exactly the same thing coming out on the other side, and sure enough, they do. If we wanted to calculate the other ones here, we could. I don't even have to do the math here because I know they come out to be the same, 1.355. Right, and therefore the mole fractions will also be the same, because if I wanted to calculate the mole fractions as an additional column here, it'd be n sub I divided by n sub t. And those will all come out to be exactly the same. So whether or not I choose the stoichiometry to be one set of numbers or a different set of numbers, so here, whether I choose the stoichiometry to be this, or I choose the stoichiometry to be, there it is, this, it doesn't matter, right? It doesn't matter in the sense that the stuff coming out of the equilibrium reactor, which is ultimately what we're worried about, those will not change. However, the intermediate values, any of those intermediate values which rely on the stoichiometry, those are going to be different. And so that's where you want to be a little bit careful. That's why I wrote this as step 0 here. It's why I pointed it out at all. It will not affect what's coming out of the reactor, but it will affect if you're sort of checking your work against something else and you've chosen a different stoichiometry, you will get different intermediate values. And in fact, you will get different functional forms, right? This product here looks like these values raised to a certain set of coefficients, or sorry, a certain set of powers. Those are not the same as if I change the stoichiometry, right? If I change the stoichiometry, now the powers are different, right? Like this one is over here. So be careful, but at the same time, if you ask me if it matters, not really, right? Technically, no, it doesn't matter what stoichiometry you choose, at least in terms of what's coming out of the reaction, or what's coming out of the reactor. There's 2 things that I would like to point out, 2 helpful tricks. Actually, there's 3. The first one, what happens if you have multiple reactions? So in multiple reactions, which is at least one of the homework problems, you will have more than one reaction occurring in an equilibrium reactor. Then you get equation 230 for each reaction. And so therefore you will also get a different extent of reaction. So if you have 2 reactions, it'll be extent 1, extent 2. If you have 3, it'll be extent 1, 2, and 3, etc. Right? And so you'll be solving multiple equations for multiple unknowns. If you have 2 reactions taking place, you'll get to write equation 2.30 twice, and you'll also have a different extent of reaction for each one of those reactions. And so you'll have 2 equations and 2 unknowns. So that's how you handle multiple reactions. This, by the way, usually necessitates something like fsolve. There's not really a way to do that by hand. There are some programs in fancy calculators that can do that, but you're probably better off with fsolve there. Next comment. Is to plot equation 230 first. The reason that I suggest that you plot equation 230 before solving is because fsolve needs a guess, right? This will give you the guess for fsolve. If you don't know what I mean by the guess for fsolve, check out lecture 1. Fsolve is an iterative procedure, right? If I'm asking fsolve to solve, this equation here for squiggle, it needs some idea of where to get started with squiggle. So I would have to somehow look at that equation and know squiggle is like close to 0.5 or close to 1 or close to 3 or something like that. How do I get that initial guess? I plot it. If you happen to know something, some physical intuition about the system, sure, you can use that as your initial guess too, but often you have no idea what that initial guess should be. And so the easiest way to get that initial guess, to let fsolve go about its routine, is to just plot the thing. And that's usually a good guess too, or a good check on your own math, because if you plot it and you see where the intersection of 0 should be, if you see where that root is, and fsolve doesn't give you that root, that's a good indicator that something has gone a little bit awry. So I usually strongly suggest that you plot it, and that will give you the guess for fsolve. And then the last question, or the last point that's on here, this is a tricky one, and sometimes it's hard to know whether you're in this regime or not, but you'll know it if you plot it, which is why I suggested that you plot it. If you happen to have very small squiggles, right? Very small extensive reaction, you may need to do something called scaling. Scaling is a way of saying, well, if fsolve is guessing values and it's looking for values that don't change the result very much. So if the answer that fsolve is calculating is around, for example, 0.667, fsolve will have tried a value just barely to the right of that, like 0.667000001, and a value just barely to the left of that, like 0.666999999, right? And it will ask itself, did I get about the same answer regardless of either one? If your number is already very, very small, if it's on the order of the step size that fsolve is looking to the left and the right, it may not be able to find that solution very well. And so there's a procedure called scaling, which is just a mathematical procedure, right? It has nothing to do with the chemical engineering or the physics or the chemistry of the problem. It's strictly for math. And so you may need to do something called scaling. The only way that you will generally know if you need to scale something is if you plot it first, right? If you're looking at the plot and you know roughly where the answer is, and fsolve is not giving you that answer, and you're like, you're 100% certain you've got all of the units right, all of the code is right, and fsolve just will not give you the right thing, then you may need to scale it. This is covered in your book, all the way back in section, I believe it's 1.8. Let me pull up the book real quick. Solve more than one reaction, scale. Oh, I don't have it in there yet. Oh, it's actually in a different, where'd you go? Okay, so the scaling actually doesn't occur until quite a bit later than I thought. It's all the way in 4.6. You'd think I would know exactly where that is, given that I wrote the book. This is actually in section 4.6. Hopefully we won't have any scaling problems on this particular homework. But if you want to read about scaling, you can skip straight over to 4.6 and read through it, because it won't, there's nothing that you need from the chapters 1 through 4 to actually read 4.6, because it's only talking about math. And so it'll give you an idea of what scaling looks like. It's just a little bit of a skip in the sections. I should make a note for that. Move scaling to chapter 1. But chapter 1's kind of already got a lot of stuff in it, right? Anyway, if you have a very small value of squiggle, then you may need to scale it. The scaling procedure basically boils down to multiply all of equation 2.30 by a big number. that's pretty much all scaling comes down to. You just make make the target that it's trying to find really, really big, which is, you're allowed to do that mathematically because it's all you're doing is multiplying the left by a constant and the right by a constant. But surprisingly enough, that's a problem that you occasionally run into. So that's a little bit about scaling. Like I said, I don't think that's actually going to come up because I don't think I planned any of the problems to have anything like that. And hey, look at that. We're at 3:51. That is class. And so what we're going to get to on Wednesday morning's lecture is just looking at exactly this again, except we'll use conversion instead of extent of reaction. You can definitely go ahead in the books or in the homework problems if you want. If you look a little bit below the section that we're referring to right now in the book, you'll see everything that we need for calculating these based on conversion instead of extent of reaction. But that is our time, so I'm going to stop talking now. I'll continue to hang out and answer any questions that you might have in chat, but I don't want to present anything more in case anybody's got another lecture at 4 o'clock. So thank you all. Stay safe. I'll stick around for a little bit and answer any questions in chat. See you on Wednesday, all. Let's get a couple of... I think I'm sharing my music right now, but let's go ahead and share that. Get some background music. It is amazingly awkward to sit in silence for a very long period of time. Yell at me if that music is too loud. You're welcome. Is there a way that you can elaborate a little bit more on plotting equation 2.30? Should we be fluent in MATLAB before we take the quiz? No, there's no MATLAB on this quiz. Although I guess if you're fluent in MATLAB, it may help you calculate things on the quiz, but it's not necessary. There are no MATLAB questions on the quiz. What is that little mark that showed up right there? That's weird. I did not write that. Yes, there is a way that I can elaborate on how to plot equation 2.30. What I mean by plotting equation 2.30 is plot this. Right, so if I were going to plot that in MATLAB, I might say something like, let xi equal linspace of 0 to maybe 2, right? Maybe I don't know where the solution is, and so I'm just going to generate a bunch of values where I think it might be. Maybe I have to change the extent of those values. And then I would say, okay, f is going to be, now I start typing all of that stuff in, right? I say 0 plus 2 times xi squared, all of the, you have to do the, it's surprisingly hard to remember how to write code by hand. Right, this and then that times the next one, 4 minus 2 times xi, take this, square it, etc. Right, and now I would be able to say something like plot xi f. This is what I mean when I say plot equation 2.30, is plot that. On the homework, how do we solve for KSC based on atmospheric pressure and other pressures? KSC is not a function of pressure. And so this equilibrium value that you get here, K sub A, it's only a function of temperature. It will never change for pressure. Pressure will come in depending on the form that you have for your activities. So for example, if you're doing a gas, the activities for gases, the forms that we're using anyway for ideal solutions, include a pressure term in it. And so that's where your pressure would come in. But KSC is only a function of temperature. Having an issue with 1.4, MATLAB's outputting values close to the answers posted. I mean, that's good. I'm only giving answers that are close. If yours are close, then that seems reasonable. Do we include the plot for guessing F solve in the homework? No, it's not necessary. It's the only way, though, that you'll know whether or not your solution is roughly where it needs to be. It's the only real check that we have on fsolve. There is a way to ask fsolve to output a bunch of its values as it's calculating, but usually those are not particularly revealing. Certainly they're no more revealing than the plot would be for the problems that we've got. And so it's more of a check for you, right? How do I know that fsolve gave me the value that I wanted? Because I'll tell you, when I look at an equation like this one, I have no idea what squiggle ought to be for something like that. I can get an estimate that it probably ought to be between 0 and 2 simply by knowing that this value has to be positive. Right, I know the total number of moles coming out can't be anything less than 0. So I know squiggle can't be any more than 2, but I have no idea what the value is in between there. If you're getting a strange value of r, you might want to carry around more digits, because r should come out to be pretty darn close to 8.314. If you're trying to plot it and you get a single scalar value instead of an array, it's probably some kind of a mistake of using these element-wise operators. That would be my only guess for a problem of getting a scalar instead of a vector. If it's particularly problematic, one way that I sometimes hesitate to say this as an option, because I feel like sometimes for loops are more difficult than it would be to do it vector-wise. But if you had xi is equal to linspace of stuff, and then you wanted to say that, say f, initially you don't know what it is, so you just make it the same size as xi and you fill it up with zeros. You can then do a for loop to iterate over each element that you've got and say that f of I is equal to, say, I forget what the equation was, but if it's something like xi, 1 minus x sub I, and you want to square that, and then you raise that to the 2, and then you multiply this by whatever the next one happened to be, 4 minus 2 times xi of I, and raise that to the squared, etc., all the way out. You could use a for loop like this to guarantee that you'll get the right number of elements. And the reason for that is because you're using indexing here to just calculate the ith element of f sub I based on the ith element of xi. Whether a for loop is easier than just reworking the vectorized code until you get it to work, I guess that's kind of up to you. Which one is more accurate? It's just everywhere where you see xi, you would have a xi of I if you're doing it inside of a for loop. Use equation 2.10 for problem 1.4d. Let me bring that up real quick. Hi, Mir. Hi. You guys want to see Mir? Mir's here. This is Mir. Oh, Mir's very sad. Mir is 13. He's a little bit of a grump. He was sleeping. Can I have a kiss? You want to say hi? Okay, never mind. All right. Let's take a look here. Equation 210 for problem 1.4. If I look at problem 1.4, part D, 900K and 500K. Actually, part D is something of a... So let me change this around and ask you, what do you think the difference will be between part C and part D? Or what is the difference between the question in part C and part D? Anybody can answer that too. I'm not asking anybody in particular, although I will, since there's only a few of us here, let's open up chat. Anybody in chat, can you tell me what the difference is between, just what are they asking for? Well, what am I asking for in part C compared to part D? Yep, the pressure changed. So then it becomes a question of, if the only thing that I'm asking you to calculate is K sub SC, and K sub SC is only a function of temperature, will the answer for part C and part C and part D be any different? Nope, be exactly the same. So I put part D on there for exactly that purpose, which is to notice that the equilibrium constant K sub A, or in this case as we're approximating it, K sub SC, is only a function of temperature. And so there will be, if you solve part C, you don't have to do very much to solve part D. You can mostly just write it down again. It'll be the same thing. The only effect of pressure is on the activities. And so the only effect there is here, right? This is the only way that pressure will come into play, is if your activity, whatever your activity happens to be, itself includes pressure. And so we see that the only one in here that includes pressure is the ideal gas. So anything that's involved in a gas phase, that's the only one that'll have a pressure effect. If, for example, I asked you to do a liquid equilibrium calculation and I told you the pressure was 2 million megapascals, by the forms that we're using, that would have no effect whatsoever. If you go to more extensive descriptions of activity, so you start introducing more and more non-idealities into it, then you can have pressure effects in ways other than what's shown in 2.1. But everything that we're doing is restricted to table 2.1. So part C for that problem doesn't have an activity because the only thing I'm asking you to calculate is K sub SC, and so activity isn't there, right? All I'm asking you to calculate in problem 1.4 are these terms. Right, I'm only asking you to calculate K0 and K1 because those are, if you multiply those together, you get K sub SC. And so if you look at the equations for K0 and K1, those are up here, and nowhere in any of these equations does the pressure come into play. And so K sub A will always be only a function of temperature. And that's not just an approximation either. It's not like, well, what if we had included K sub 2, right? K sub 2's got a bunch of stuff in there. Maybe these heat capacities are also functions of pressure. Maybe someday I might have to worry about that. That's actually not the case. The heat capacities there for gases, or I should say, just the way that we've written heat capacities here, those are only functions of temperature. In fact, they're defined to be only functions of temperature. So there will, it's not like I'm holding back and saying, you know, someday it'll be much more complicated and you'll have to do pressure in your K sub A calculation. There will never be a time where pressure ever enters into a K sub A calculation. It's not part of K sub A. It's only a function of temperature. So when you're looking at the homework problems, at least for problem 1.4, for problem 1.4, I haven't asked for any of the activity terms. I've only asked for K sub A, or in this case, K sub SC, and so you won't have any pressure terms. think I'll give this questions maybe, I don't know, another minute or two. And then I'll get started on posting these, this lecture. That seems to be all the questions that we got. So I'm going to wrap it up. For anybody still here, thank you very much. And for everybody watching the video, thank you very much. And we'll see you on Wednesday. Bye all.